Hello everyone, I'm Mahendrini, a final year PhD student at University of Cambridge, and today our paper is about generating railway geometric digital twins from airborne LiDAR data. First, I'm going to talk about the background of the study, highlighting the need of generating railway geometric digital twins using automated methods. Digital twin is the digital replica of a real-world asset. So in our research, we define the term geometric digital twin to represent the fundamental 3D geometry in IFC format generated using airborne LiDAR data. This is beneficial for rail inspection, maintenance, and practices, which usually require substantial costs and timescales. So railways are complicated, safety critical systems occasionally face catastrophic risks with costs around £3.4 billion each year. Near real-time maintenance, safety management, and retrofitting are therefore vital operations in the life cycle of existing rail infrastructure. However, when we look into the current maintenance processes, they can no longer cope with the increasing complexity of their systems due to the absence of digital twins for current assets. So the digital twinning process automation would reduce the modeling time and eventually save on costs. This explains why there is a huge market demand for less labor-intensive railway maintenance techniques that can efficiently boost railway operations and productivity. So with that aim in our mind, we focus on automatically generating geometric digital twins for railway track structure and superstructure elements. Our proposed framework starts with the raw railway point cloud data and contains three phases. The first process is the automated removal of noise points and mass segmentation. And the second process is the generation of overhead line equipment geometric digital twins. And the third process is the generation of railway track geometric digital twins. Prior to defining the objectives of the research, we have analyzed the existing railway element segmentation and modeling methods. For mass, we considered pole segmentation and modeling methods not only for rail infrastructure but also considering road networks. From the background study we carried out, we could see that there are specific limitations exist. To name a few, mast and other pole-like object segmentation and modeling methods usually depend on the scanner profile information. And majority of these methods does not provide automated solutions for the detection procedure. Also, some methods fail to distinguish trees from mass. Therefore, we conclude that there is no solid approach to segment and model railway mast automatically from airborne LiDAR data by satisfying all user requirements mentioned in our paper. For overhead element segmentation and modeling, the challenges inherited in point clouds, such as data gaps in the cables, vegetation, and bundle cables, reduce the accuracy of the results of the existing methods. Many of the methods are sensitive to the voxel sizes, threshold settings, and point densities. A few studies overlook the sagging of the cables, while others assume that cables are series of small straight line segments and that cables are always parallel. Overhead elements are very thin and therefore are often represented with few to no points. The segmentation of overhead elements is difficult due to the presence of vegetation. These factors make the methods mentioned in the state of research unproductive for different use cases without any prior information about the scanner profile. Finally, we have analyzed the existing rails and trackbed segmentation and modeling methods to better identify what gaps exist in the current state of practice and the state of research. So railway geometric modeling in the literature has focused mostly on the rail detection using laser scan profile information. However, the existing methods cannot offer large-scale digital twinning required over kilometers without forfeiting precision and manual cost. They only work well in much shorter track segments, on average 300 meter, or simplified cases without complex geometries as bridges, tunnels, and crossings. Besides, the real railway point clouds often encounter huge challenges such as occlusions caused by vegetation around the track and unevenly distributed points. These characteristics complicate the modeling, which is why none of the existing methods can manage them reliably. So based on the literature we carried out, we identified gaps in the knowledge related to the segmentation and modeling of the railway track structure and superstructure elements. The main hypothesis of our research is that the use of railway topology has the theoretical potential to perform better when segmenting and modeling the geometry of railway elements in point clouds with varying geometric patterns. We have tested this hypothesis with three approximately 6 km long point cloud datasets, which means 18 km in total length. Railways are linear asset types with standard geometric patterns, so their geometric relations remain roughly unchanged often over very long distances. The close inspection of railway point clouds validates this effect with repeating geometrical features. So we use these features as assumptions in our proposed framework. A railway point cloud is usually given at an arbitrary position and orientation. So the idea is that prior to any subsequent steps, we first needed to align the pose of the railway parallel to global axes because all features to be extracted in further steps lie in a global coordinate frame. To achieve this, we first align the rail track by chopping the whole dataset perpendicular to its principal direction. That step was also needed to remove the vegetation from each of these small units. So once all the noise points are removed, the only vertical element parallel to Z-axis should ideally be mast. So we used a line detection method to detect mast as lines. However, as there were few other remain tree trunks and few vertical objects close to rail track, the detection results were not sufficient enough to extract mast as point clusters. So we followed two refinement methods to sort mast from other pole-like objects. In here, we first took the top-down point densities to sort mast from tree trunks as given on step 3. So when we get the density ratio as a threshold to sort mast, we could filter most of the mast from the trees. However, to increase the accuracy, we needed a second refinement which took the railway topology knowledge. This refinement could search mass pairs over the regions along the track where we could positively expect masts. We used the resulting aligned and narrowed railway point cloud datasets and mass position coordinates of our previous step as the input data for the second process of our framework. So first step of our method automatically extracted the point clusters of the overhead elements. This whole unit is hereinafter known as C-section. So we used a crop box filter to extract the point segments of the C-section. This filter automatically extracts all the data within a given cube in 3D space by removing any points that do not satisfy the given parameters of the cube. Secondly, we extracted point clusters of cables using Ransack algorithm, which consisted of two refinement algorithms. These refinement algorithms first divided the whole point cloud dataset into near straight pieces and then removed the ground plane and finally upsampled the points on the cables to reduce the computational cost and to increase the detection accuracy. Next, we generated different configurations of parametric models of overhead system elements, which represents widely used existing overhead system configurations in Europe and UK. Our algorithm automatically converts these models into points. So now we have different configurations in point cloud format. The algorithm then used iterative closest point algorithm to find the most suited configuration and the best possible fit. This finally produces the transformation matrices that provides the rotation and translation related to each C-section and cable segment. Applying this to original IC model, we could finally generate the geometric digital twin of the model as one system. The first step of the third process of our framework is separating ground points, including horizontal and quasi-horizontal planes, from the point cloud dataset. This is essential as it permits segmenting points associated with rails and track beds from the railway point cloud. It allows one to easily exploit the linearity of the rails against the ground using linear feature extraction algorithm, and also it minimizes the effect of false positive that may arise due to other linear elements such as overhead cables, and finally it significantly reduces the number of points required for the rail and trackbed segmentation method, leading to faster computational performance. For these purposes, we use transact plane detection, and after this step, we assume that only linear element on a segmented unit now represent rails, while the rest of the points on the box represent track bed points. Using Ransack, 4 lines which represent 4 rails in a double-track railway with maximum inliers are then iteratively generated by determining the most probable hypothesis line for each unit. We initially assumed that the points on the segmented unit represent rails and track beds only. This means that once we remove the segmented rail point clusters from the crop box, the rest of the points represent trackbed point cluster. So the previously segmented point clusters are now known as model A's. Next, we design pre-assemblies of track structure elements, herein known as model B's, using standard railway guidelines to represent the geometry of the real track structure elements. These models preserve the geometric properties of the elements, such as different web thicknesses, head widths, in rail profiles. The method then used the iterative closest point algorithm to automatically converge model B's to model A's. So we set model A as the reference cloud here, which is kept fixed, while different profiles of the model B's are source clouds. So the method first converts model B into point cloud format, and then these source clouds are transformed to find the best match with the reference cloud by minimizing the distance between the two. Finally, all transformed models were combined to obtain one system representing superstructure and track structure elements. To evaluate the accuracy of our framework, we manually generated 2 sets of ground truth datasets consisted of 3 sub-datasets, each for 1 railway point cloud. So the first set is manually extracted point clusters of track elements, and the second set is manually generated models which were used to compare against the automated ones. We use precision recall and F1 score metrics to assess the segmentation accuracy and cloud-to-cloud distance evaluation to detect changes between the ground truth models and the automated ones. Initially, we converted the ground truth models and the automated models into point cloud format. The evaluation method computed the root mean square error between the each unit of automated models of track elements and the corresponding ground truth models. The average model distance between the two for all 18 km were 3.82 cm root mean square error for railway superstructure elements, 3.38 cm root mean square error for rails, and 2.72 cm root mean square error for track beds. The proposed method reduces manual twinning time by 90%. So this implies that our proposed framework outperforms the manual operation, fulfilling the main objectives of our research. To conclude the presentation, I would like to highlight main outcomes and key contributions of our research. Our framework is novel automated data-driven and model-driven method that exploits highly regulated and standardized nature of railways to generate geometric digital twins of rail infrastructure. This method can deal with real railway point cloud, consists of varying track slopes, curvatures, and crossings, and it is also effective in handling challenges inherited in point clouds such as occlusions, extreme vegetation around the track elements, and local variable densities of points. Also, our method still provided high segmentation rates and can correctly represent the geometry of railway elements despite the different geometries appears on the track such as overbridges, tunnels, and crossings. This method offers significant computational cost reduction by automatically cropping a lengthy railway point cloud into relatively straight segments. This enables a considerably improved large-scale object detection generally required over kilometers without forfeiting precision and manual cost. Therefore, we conclude that this is the first to automatically and robustly solve the generation of geometric digital twins of railway track structure and superstructure elements from railway point cloud data by exploiting repeating railway geometric patterns which lengths over kilometers of spans without needing any prior information about the input dataset. So thank you for your attention.